Okay. So first of all, thanks for the invitation to be here. It's been a very productive time for me. And I see that Newton Institute is very well organized. I see that Catherine does all the work for this particular semester. Anyway, it's been very enjoyable. Also note my collaborators here, if they're not explicitly mentioned later. So, I mean, this encompasses a lot of different directions of work, so that's why there's so many collaborators. So here's the problem I want to talk about. We have a parametric family of PDEs. Y is the parameter, U is the solution for that parameter, Y. And I'm in a setting where I have a certain state, U of Y star. I don't know Y star, but I'm going to observe some data about U of Y star, right? Some measurements, linear functionals applied to U of Y star. And that's the information I'm going to have. So I know the PDE, I know the general form of the parametric PDE, and I know this data. And my question is, how well can I estimate Y star? Of course, this kind of a problem occurs lots of places. We drill oil, we want to understand the media under the ground, and that would correspond to some choice of parameter Y star for our model for the terrain under the ground. Now my interest, my philosophy in approaching numerical problems is to first try to understand what is the optimal performance we could possibly get. You know, before we start creating numerical methods, what's the best we could possibly do? And then once we have that in hand, try to create a numerical method that performs at that optimal performance or near the optimal performance. Because if we do that, then we can be sure nobody's going to come next week and say, look, I beat this. Whatever DeVore did, look, I can do better. So that's the way I'm going to attack this problem. Now the first part of the talk, I'm going to look at the question, suppose I knew fully the state U of Y star, not data about the state, but fully the state. What could I say about Y star? So that's part of the problem, because I'm going to only have partial information about the state, not full information. And then the second part, I'll come back to this question where I have partial information.
So I didn't get the first part. So you know complete state, what does it mean? You know U of Y star.
I know U of Y star, yeah. So given Y, you create a U.
Yeah.
And I want to know that Y, but I only see the U. Can I, so it's an inverse problem.
Yeah, but
right?
you have also PDE which connects U and Y.
Yeah, that's the map. You have a forward map that given Y, you determine U of Y, and then you're really interested now in the inverse map. Given U of Y, can you determine Y? Go backwards. You with me?
Yeah, but if you know U, then
No, but you don't know the parameters.
You
You
don't know
can't
the
solve the
parameters?
forward problem. You don't know the parameters.
If I have a function and I
You
tell
know
you
it
it takes
solves
the
the
value 2, can you tell me at what point it took the
no,
value
but if you have
2?
that PDE, then that will mean that you will have a PDE with respect to Y star, right?
But there can be many Y's that give me the same U of Y, a priori, right?
No, but he has a PD and he doesn't know the coefficient, for example. He knows what he's saying is, I know the solution, but I don't know the
Forgive
coefficients.
Alexei, I mean, he's not in this world, okay, of this particular problem. He's in some
I am
other
in the
world.
world.
Okay. Now, you know, I'm interested in very rigorous theory, so I'm going to position myself in the most friendly situation. Everybody does take some toy model problem and says, let's look at that. And then if we can understand this problem, then we can branch out into more a general setting. So I'm gonna look only at the following elliptic setting. So I'm gonna have a parametric family of elliptic PDEs. They're of this form, minus divergence A grad U equal to F. F is gonna be fixed and known to me, zero boundary conditions. And I have this family A of diffusion coefficients. These are the parameters in some sense. Even though I used Y before, think of the diffusion coefficient as the parameter. Now, in order to guarantee existence and uniqueness, I assume this uniform ellipticity property, that there exists a little r and a capital R, and A is always strictly positive. So at this stage, the A's are quite general, right? Because it can be any L infinity function, which is strictly positive. So you should be cautious here. Now, given any A, there is a unique solution to the PDE, UA. And as we look at the mapping A goes to UA, this describes a manifold UA. The set of UAs, the images, as we vary A over our set of diffusion coefficients, right? So we picture this, that we have some solution manifold here, M. Okay? So UA lands in M. And this is a subset of H1, functions with one derivative in L2. Okay. So capital F here denotes this forward map, this solution map. Given A, we determine UA. Okay. Now, it turns out that to prove rigorous results, you'll generally have to assume a little bit more than just the setting I described, where A is just simply an L infinity. You have to have a little more structure for A. And I just want to point out two of the common settings. One is this so-called affine setting, where you assume that the diffusion coefficients are some mean plus perturbations. And the yj's now are the parameters. And we can normalize them so that they lie at -1, 1. This is always possible. And here the psi j are some functions, maybe a coherent expansion or some wavelet expansion, or polynomial expansion, whatever you have here, the psi j's. Okay, so my set of parameters in this setting would be -1, 1, and I don't assume that the parameters are finite in number. And the reason is I want results that are immune to the number of parameters. And if I stick in D and start getting results that depend on D, I don't like that. So we treat this as if there are an infinite number of parameters. If they're finite, it's okay. So the typical theory, if you want to then understand the solution map and properties and how to numerically capture this forward map, it usually involves some assumptions on the psi j's. And the typical assumption is that the psi j's, their L infinity norm, decays at a certain rate. If you say that it's an LP, then it means that the jth function is less than j to the -1 over p, right? So this is decaying at a rate a little faster than 1 over j. Okay? This means that if you look at the diffusion coefficient, the influence of later terms in this expansion are less and less, right? Because the norm of psi j is getting smaller and smaller. Okay, the second class of examples that I'm going to engage here is, so forget now affine and just say, let's put some smoothness on the A, the diffusion coefficient. And so I'll measure smoothness in the Sobolev spaces HS which are the L2, S derivatives in L2, right? That's what HS is. So we know that we have a function in L infinity, but this will, in general, impose more structure on A. So typically, the assumptions on S are smaller than 1, but at this stage, I just introduced this class, so this AS means that in addition to assuming that the A's are in L infinity, I assume that they have some regularity in this L2 scale. Okay. So, remember my first question was, can I determine A from knowledge about the image UA? So I have this forward map that takes my parameter, maps it into the solution UA. I observe UA, can I determine A? Well, that's the question. Now, this is going to depend on the right-hand side F. Now, notice in contrast, if you're familiar with like Calderon's problem and that, I have a fixed F. I'm not allowing four things to, that would be a different problem for me if you allow different F's to be injected. If you're trying to understand some flow underneath the earth, you could keep injecting different force fields, but I'm not doing that. I have a fixed F. Okay? And you can see very easily, and you all know this if you're in this field, that if you have an A for which grad UA vanishes on some open set, D0, this is your physical domain, D. And if grad UA vanishes on here, then you can change A anywhere on D0, and it won't change the solution, right? Because on D0, changing A to B, you'll still get 0 on D0, and if you don't change it outside D0, you will still get the same solution. So, and of course you can always construct such functions. Just take the U that vanishes on some set D0 and define the right-hand side F to be the operator applied to that U, then you'll be in a situation in which you don't have uniqueness. So I want to avoid this, and I can avoid this if I assume that the right-hand side is doesn't change sign, doesn't vanish on a set. Because if grad UA vanished on a set, then obviously the right-hand side will vanish because you've got the divergence of grad UA, so it would vanish. So this is the assumption I'm going to make on F throughout the talk. That is strictly positive. And I need that, or I can't say that there is a unique A that determines UA. Now the question is this enough? If I have this condition, is this forward map, or does this forward map have a unique inverse? So that's the situation I'm in. That's the first question I want to understand. You would think elliptic PDEs have been studied, right? Ad infinitum, that you would know the answer to this question. We'll see that we don't know the answer to this question. We know quite a bit, but not the final resolution. Okay, so before going to further into the inverse map, I have to discuss a little bit about the forward map, why it plays a role in this whole thing. Obviously, you're worried about two guys completely different collapsing into one guy. So anyway, we're going to need some results about the forward map and the stability of the forward map. So this isn't the inverse map now I'm going to talk about, it's the forward map. And I'm going to say, what happens if I take two diffusion coefficients A and B, if they're close, can I say that UA and UB are close? in H1. Well, this is rather classical. The typical result is, yes, they're close. In fact, you have a Lipschitz dependence, what I call Lip1, that you can estimate the H1 deviation between UA and UB in terms of the deviation between A and B and L infinity. And you have this constant, and this is a graduate student exercise done in every class that talks about elliptic PDEs. Now,
Is little r is the lower bound for?
yeah, little r is the lower bound for the coercivity, and the right-hand side at this stage is any function in H minus 1, the dual of H1. Okay, in our business now, we're gonna turn to the inverse map, but even if you were interested in the forward map, this inequality is not completely satisfactory. Why? If I took an A and a B, which are discontinuous, and if their discontinuity doesn't match, think of two piecewise constant functions. And if the discontinuity doesn't match, this right-hand side is gonna be 1, right, or a constant. It's not gonna be small. Even though A and B may agree everywhere, but on a little piece, this thing blows up. So this isn't good. And this happens in several applications. So the question is, are there better ways to measure the stability of the forward map than this inequality? And the answer is yes. And here is a result that proved with Andrea Monito and Ricardo Nochetto, that you can estimate the deviation here in terms of not A minus B and L infinity, but in an LQ norm. Ah, good, because in LQ norm, two discontinuous guys, their norm can be small on LQ, it just will depend on the measure of the set where they deviate from one another. So that's the good news. Okay, great. You see, you have a nice inequality. The bad news in this inequality, which will be removed in a moment, the bad news is I have to have an assumption here. Here I had no assumption on A and B. Here I have the assumption that the grad UA is in some LP, which is related to Q. So if I want this inequality, I have to know that for the A I'm looking at, so you can fix either one of these as A and the other one let vary, that I need to know that the grad of UA is in LP. But I'm telling you, we're gonna remove this in some sense. You may be unsatisfied at the moment, but don't worry, it's gonna work out.
Sorry, can I ask you a question?
Yeah,
So if we knew that the grad of UA was in L infinity, so say we just impose some stronger assumptions on
Yeah.
all the coefficients.
then we get this result.
But could we
Well,
get
no,
could we
excuse
get
me.
the L2 on
If
the
we
A
had
minus
just
B?
grad UA in L2, we get this result.
Right, and if we put the P equals infinity, would we get Q equals 2 without the additional
Yes.
exponent theta?
Yes.
Ah, okay, great.
Yeah. In fact, I'm interested in the case Q equal to 2. So I mentioned that from this, if I have this, and I always have an inequality of this form in L2, with the right-hand side in L2. And the reason is that I know that not only is A minus B in LQ, but I know this in L infinity. So you can always estimate an L2 norm if you know the function is in, excuse me, you can estimate the LQ norm in terms of the L2 norm for Q bigger than 2, utilizing the fact that it's A minus B is in L infinity. You all see that, right? Integral of A minus B Q, you take out the Q minus 2, right? You take out Q minus 2, and that becomes just some constant, because you know that A minus B is in L infinity, and this is less than or equal to the norm of A minus B in L2 to the 2 over Q, right, or something. Okay? All right, so you can, so whenever you have this situation, you will have, whenever you have this situation, you'll have this type of an inequality. And your question was related to what is this theta? And the answer is that yes, if you had Q equal to infinity, you would have theta equal to 1 here. You would push theta to 1. In general, when Q is less than infinity, you'll have a theta smaller than 1. Okay? All right.
Sorry, Ron, could I ask a question? Perhaps it might help any statisticians in the room. So we've had a lot of statistics talks about sort of Gaussian process emulation.
Yeah.
And I'm not an expert, but if I understand the approach right, you have you model the output of your model or your computer model as a Gaussian process, and you pick a covariance function, which essentially describes your belief about how the output of the model for 2 different choices of the inputs are related. Is that so? So of course, if you do this, you have to choose a covariance function, which encodes sort of your belief about the input to output map. But I guess here is kind of a situation where we have a very specific model. It's not yet a computer model because it's just a PDE. These results tell us something about how close, I guess, 2 solutions corresponding to 2 different inputs. So is there a way to somehow
So
connect the
I won't answer your question. I'll be like a politician. I'll answer some other questions.
Okay.
No, so my reaction, having seen several Bayesian, for example, talks, was I never see where they're explicitly utilizing the properties of the smoothness properties of this forward map. See, this forward map is very smooth. I just put down that it's Lipschitz in the sense of L infinity diffusion coefficient going into the H1 solution. It's Lipschitz map. But it's actually an analytic map, and I don't see them utilizing this. Now here I'm on the deterministic side, and I forget the randomness and the benefits of averaging out random behavior. And I say, well, let me understand deterministically what's happening. And so I'm focusing on this smoothness. And I think the real world is to put both together somewhere. That was my dream coming here. And we did talk to some people which are moving toward putting this all together. So I didn't quite answer your question, but said something that maybe you'll let me proceed. Okay. So here's a little bit more information about this, because remember I have this condition that, I need. That I needed to have that the grad UA was an LP, and you could say, whoa, yeah, great, he has some result, but he has this condition, grad UA is an LP, how would I ever know that? Well, fortunately, there's a large literature on elliptic equations, and this is a well-studied problem, and I just want to mention a couple of results to tell you what is known. So for one thing, it's known that there's always a range of P bigger than 2, with no other conditions on A. Just that it's in L infinity. Back to what our general setting was, there will always be a range of P between 2 and capital P. This capital P will depend on the Lipschitz domain, and the results of this are obtained by looking at perturbations of the Laplacian to get such a result. But anyway, what one ends up with is that there always is a certain range, where you have that grad UA is an LP. The range may be P, little p close to 2, which you don't like. You want to have little p as big as possible. That gives you the most smoothness. But you'll have a range very close to 2. Remember when we started, we only knew that p equals 2 was certainly the case, right? Given, we always know grad UA is in L2. UA is in H1, grad UA is in L2. And this result is saying there's always a range close to 2 where you have grad UA and LP. And this gives you automatically an inequality like this with some theta. So you always have a smoothness here, a stability, now not from L infinity to H1, not assuming A and B are in L infinity, but A and B are in L2. So there always is a theta. Could be small, but there is a theta.
So you're only assuming that F is an H minus 1 here, or where? Or what?
You only need in this case that F is an H minus 1. Later, when I get deeper into this, F is going to be an L infinity function, strictly positive, because remember I have that question of what does it mean that function in H minus 1 is strictly positive and so on. So, but at this stage of this general theory of forward map, F is anything in H minus 1. Another result, very close to your question, is the following, that if A is in VMO, not L infinity, you know, you have BMO, which is bigger than
So
L
what does
infinity.
that stand for?
Uh,
VMO? What does that stand for?
Vanishing mean oscillation. Do you know BMO? Bounded mean oscillation? Oh. You need to learn BMO because, you see, if you study harmonic analysis, or even PDEs, usually when you're studying PDEs, you have a problem when P is 1 or P is infinity. If you study harmonic analysis, you study how does Fourier series behave. You have a problem when P equals infinity or P equals 1. And a result that may hold for all LP between 1 and infinity breaks down at P equals to infinity. That's usually what happens. BMO is something close to L infinity. In many theorems, for example, the Hilbert transform is bounded from LP to LP, for P between 1 and infinity fails when P is equal to infinity, but it holds for BMO. The same thing on the other side is H1, not your H1, but the Hardy space H1, it's bounded on H1. And this is a better description of what the properties of these mappings like conjugate functions, Hilbert transforms, singular integrals. You know, maybe you know a little bit about singular integrals, Calderon-Stein theory, yeah, okay, anyway.
Yeah.
So BMO is a bigger space than L infinity. Not too much bigger, but a little bit bigger. I could define it, but then we will really have a 2-hour lecture. Anyway, you need to Google BMO. Okay, and VMO is just a little bit stronger than BMO. Huh?
So what you're saying here is that F is an H minus 1, the domain is Lipschitz,
Yeah,
and I assume you got 0 boundary conditions.
yeah.
And you're saying basically the solution then is in.
It always
some-
has a
is it
Lipschitz,
some
what I
W-
call
is it
lip theta.
W- Is it W1P with P bigger than 2?
Yeah,
That's what you're saying?
That's this
what
result.
proves, yeah.
and this
Okay.
result is saying it's
Yeah.
in W1P for all P less than infinity, okay?
Yeah.
So these are results in harmonic analysis or elliptic PDE theory. Okay, but the important thing here is, whoops. The important thing here is that if I go, instead of assuming, here I had no assumptions on A, none at all. This always holds. When I start to make assumptions on A, I would still like to handle cases where I have discontinuities. This would allow me to handle discontinuities if A is in VMO. However, it doesn't handle jump discontinuities. function with jump discontinuities is not in VMO. So then you don't ask me, well, what are functions with have discontinuities but not jump discontinuities? Go back to your calculus, okay? Anyway, all right, so I'm going too slowly. Let's now, so that, the forward map, understanding the forward map. The forward map always has a certain Lipschitz smoothness, and by assuming some regularity for the diffusion coefficient, you get more smoothness. Okay, let's look at the inverse map. I'm interested, remember in the question, given UA, does it uniquely determine A? First question. Second question would be, if it does, what's the smoothness of this inverse map? Now you can imagine that when you formulate such a question, the first thing you're going to do is look at the case of 1D, because you can write down the solution, right, very simply as an integral in 1D. And if you do that and go through this exercise, here's what you find. You find indeed, okay, first of all, this is the forward map, that the behavior, there is no theta, and this holds for every A and B. So suddenly I removed the theta I needed when I went to higher dimensions. But secondly, I have this inverse map, that in fact the inverse map is unique. Given UA, there is a unique A. Not only is it unique, but I have the stability that if you perturb UA, if you have UA and UB are close, the A and B are close. And how close are they? There's this power of 1/3. Okay, so this I call Lipschitz 1/3 smoothness of the inverse map. Notice I'm measuring smoothness here in L2. If I didn't measure in L2, I would have a problem. I'm measuring how close they are in L2. This 1/3 cannot be improved. And you look at this result and you're quite happy. You know the best you know the best smoothness and everything. So in 1D, everything is fine. You're very happy, and this sort of motivates you, right? And you say, well, wait a minute, I can do it in 1D. Let's do it in D bigger than 2. So when you go to higher dimensions, it gets more complicated. And I'm going so slowly here. I just want to, so let me tell you what happens in higher dimensions. Two things. First of all, we do not know whether, under the assumption F is positive, whether UA uniquely determines A. You would think, I go to all the elliptic guys and ask them this question, they will say, oh, come on, this is the answer. So, you know, I send emails to my friends in the elliptic community, and like usual, you get an answer that doesn't answer your question. They say, oh, I'm glad you asked me. Let me tell you, I just did this in my recent work, and they quote some result, and you look at the result, and it isn't the answer to your question. It's usually a Calderon problem, because this is what's dominating their thinking. Okay, so we don't know the answer to that question. My guess is that the answer is no. But we don't have a counterexample yet, and we haven't worked too hard on it. However, what I can prove is if you start to assume a little bit more about A and B, a little bit of regularity, then I can prove that the inverse map is unique. And in fact, you have a stability. So this kind of a result holds and for D bigger than 2. The exact value of beta is going to depend on the additional regularity you're going to impose on the diffusion coefficients. Okay?
And can you similarly show that it can be improved? Or
No.
like in the 1D case?
No. 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 You see? You're too greedy. No, I'm with you. I would like to do that, but it becomes quite involved just to get this kind of a result. And there's no way I can see from our proof that we have optimality in the beta. So I know there is a beta. I can tell you the size of beta, but I can't can't tell you if the result is optimal. Okay, here's some discussion about the values of beta. You can already see it's not optimal in some sense. Well, if the diffusion coefficients are in H1, then I can prove beta is 1/6. If the diffusion coefficients are not in H1 but in HS for S less than 1, then I start losing. I lose something in the beta. And in this result, you assume that they're in HS, but also in VMO. You can drop the VMO requirement, and I guess this is the main result, that if you assume A and B are in AS, then there is some S star less than 1 for which you know there is always a beta. You have uniqueness in the inverse map, and you have this Lipschitz beta smoothness of the inverse map. Okay, so the main thing here is that you have to assume a little bit more regularity on the diffusion coefficient A rather than just assume it's an L infinity. You have a little bit of regularity, but it's not severe regularity. We're not assuming it's continuous or anything real great. I mean, it's HS, S, typically bigger than a half. Why bigger than a half? Think of the trace theorem. That seems to be the role of 1/2. By the way, if you apply these results to piecewise constant functions, you don't get this stability, but you can directly prove that if you have piecewise constant functions on a partition into n to the d cubes, this is often used in simulation, right? You take your parameter domain and divide it into small cubes and have piecewise constant on here. Then you do have unique determination of A, right, from UA, and you have this inequality, and what's hitting you is this n here in front, but it's a fixed constant if you fix n, the number of cubes. Okay, so that's what I know about the inverse map, and to summarize, I do know that the inverse map is unique, and I do know it's in some Lipschitz beta, provided I add a little bit of regularity assumptions on the diffusion coefficient. And in answer to your question, do I have the optimal result? I don't know whether what I'm adding to the on the regularity is too much, too little, and how it matches the beta. We don't have that perfectly sorted out. Okay. So this is a summary of what we know. We know the forward. We know two things. We know the forward map is always smooth, or any A, B, no conditions on, whoops, wow.
Very sensitive.
Oh, wow, I see. So yeah, I have to go back, I see, but I'm worried about the time, because I like this atmosphere of, you ask a question, we can get to talk about it. But if you're worried about me finishing at 12, that's a problem,
I'm not worried.
okay?
I'm not
It's
worried.
completely
Well,
up to you.
if you need to leave, just go, right? I'll try not to go on too long, but I like to go at a pace where everybody's happy.
Can I ask one last question, or maybe later?
No, you can ask.
Just regarding the forward estimate
Forward
for
map.
the forward map.
Yeah.
The constant c in front. So
Yeah.
that would blow up if we let the lower bound on a tend to 0, right?
Oh, yeah.
But I was wondering, what exactly does it depend on? Does it only depend on the lower bound, or does it also depend on the capital R, or is it universal in?
This is interesting. It does depend on capital R, but
Oh, I see. Okay.
capital R is arbitrary. No, it doesn't depend on capital R, excuse me.
Uh-huh.
So if you look at the original results I had, yeah, this is why it becomes interesting. Here. You see capital R is not appearing here.
I see, yeah.
Look at this, right?
Mm-hmm.
Well, it's appearing only in the sense that, you know, you need A, B, and
Sure.
you could have it there. So that's why it's sort of interesting that in Lax-Milgram theory, you need a capital R, but it doesn't appear when you do these kind of estimates, which is a little strange to me. You should think that it would pop up in an inequality of this type. The same holds when I go to these finer inequalities that I've discussed about L2, okay?
Mhm.
Okay, now, see if I get back to it. All right. All right, so this is a summary. We always have a smoothness for the forward map, and we have a smoothness for the inverse map, assuming a little bit more on the diffusion coefficients, all right? By the way, this discussion of the inverse map does not give me a numerical algorithm. If I had UA, it doesn't tell me where, it just tells me A is unique, doesn't tell me how to find A. The usual way to find A that people use is they use some discretization of parameter domain, right? They take the parameters and they discretize, let's say finite elements or something to represent the A's, and then search over this discrete parameter domain for a guy which matches you know. Wow, this is so, for me, anyway, sensitive. So you search over your discrete parameter domain for a solution that's close to UA. Then your stability result tells you that your A hat is close to A, right? So this is the usual way numerical algorithms work, but we're going to get into that in more
From
detail.
may I ask you still a question which I was asked at the very first minute?
Yeah.
So you have a PDEs which involves A and UA, yeah, and
Yeah.
you know that UA now is, we know the full state, yeah?
Yeah.
So we just put this UA into the PDEs and then you get PDEs with respect to A. Now A is unknown and UA is known, yeah, so, I mean, now you
Yeah,
have,
this-
now you have the same problem as initially, now it's only A is
Yes.
unknown, and then the problem is stability or whatever with respect to now UA are coefficients, yeah, so.
Yeah, people do this. This is writing an equation for A as a transport equation, right? And this is one way of saying, okay, I'll find A because A, if you look at the PDE for A, when you do this substitution, it becomes a transport equation. The problem is in transport equations, as soon as you have discontinuity in the velocity, you have a problem. And this is why, if you look at the literature of the people that are using transport equations in this way, they never get to find results. They always have too much smoothness assumption on A and too much smoothness assumption on UA. Because they want to put themselves in the world where the transport equations are, I'm trying to think of the Russian guy who's famous for all the transport equations, his name escapes me. But that's the answer to your question. That's why it's not done that way, or at least the results you obtain that way are too restrictive, okay? All right, now I go to the second part of the talk, where I'm given partial information, right? And after asking questions, you can't look at your watch. If you ask questions, you can't then go, huh? Okay, so now I have this partial information, I want to see what I can do. And first thing you have to do is, you have to be very careful, is to formulate correctly or what do you mean about recovering A? Because if you have partial information, A is definitely not uniquely determined. There'll be a lot of A's that satisfy that. So what do you mean you want to recover A? There's not a unique A. And I'm going to give you two settings. One will be, of course, resolution and the other a finer resolution. So here's my assumptions. I have these linear functionals, which are applied to UA that give me the data, right? And these linear functionals have Reese representers and can be represented by inner products with guys from H1. And you can view the information you have as giving you a projection of UA onto some subspace of H1, spanned by these Reese representers, W. That subspace, of course, the more data you get, the bigger that subspace gets. Starts to fill up all of H1 and you're in better and better situations. Here, I'm not, obviously, the more linear functionals I have, and the form of the linear functionals, that is, how they look is gonna be important in this problem, because you can have bad information and you can have good information. I can give you data, I can give you, if you have a function on 0, 1, and I give you all the values near 0, I'll be giving you a bazillion values, but it's not very useful to you because you don't know what's happening elsewhere. Same thing happens here, but I don't, and we understand this well, but I don't want to get into that in this talk. Okay, so this is my setting, and okay, so now we're in a situation where we definitely don't have uniqueness. That is, the data here, W, that I measure, definitely does not determine uniquely in A, right? Because W won't determine uniquely a state. There'll be many states with the same measurements, and any of these states will have an A or B associated with them, so you're not gonna have uniqueness, so you have to be careful. What do you mean by then recovering the parameter? So I say here's my formulation of this, okay? So I know I don't have uniqueness, so what am I going to say? So maybe to draw a picture, you have here in parameter domain, right? This is your parameter domain A, and you'll have many possible A's that give rise to your W. So what are you going to mean by an algorithm and a success? Maybe it'll be easier if I talk at the blackboard rather than read this. And it may go faster.
That can't be recorded.
Oh, it can't be recorded? Okay, so I don't do that. All right, so one way, so I'm now trying to understand what would be the correct formulation of a recovery algorithm for the parameters. In the Bayesian world, you know, you start with a probabilistic distribution for the parameters, and then you have the so-called prior distribution, and then you say, well, what can I say about the posterior, which is sort of zeroing in on what the parameters could have been for your problem. I'm trying to do it in some deterministic way. I had all possible parameters. Now I make this observation. What can I say back here about what was possible for the parameters? So first thing I do is, which I don't want to pollute things by this, but I look at this set of parameters for which you don't get the value W exactly, but almost the value W with an eta. Why? You can imagine numerical reasons, and no algorithm is going to be able to find exactly all the guys where this is 0, right? That would be all the parameters B, which you're looking for. So you introduce this eta, but you can make eta small, and then I'll begin my work, okay? All right, so that's the reason we have this eta. So now, I say there are this is the first way you could say how to capture A. And that is what I call the smallest ball. So I look at all the parameters that, let's say, give the value W or are in this SW eta, where eta is small. They're very close to giving the value W. and I say, find a ball here in parameter space that contains all these parameters. Find the smallest ball. Let me erase this one. Right? This would be the smallest ball. If I take the center of the ball, it provides an approximation to all the parameters that satisfy the data. No other one approximation can do better. This is the best you could do if you're interested in saying that A star minus something you computed is small. This is the best you could do. This I call the small ball. So that's a coarse resolution of the parameters that map into W. Small. A second formula, so there's a pictorial of it. The pink guys are all the parameters that mapped into W. And then I have this ball, and its radius is the best I could approximate all the parameters. And the center is the approximation I would use. Got it? Okay.
It doesn't necessarily give you W, right?
The center doesn't necessarily give you W. But you could,
It's
you
an
know, if you,
approximation.
well, already with that SW eta, I said, Max, give up on trying to find exactly W. You know, you'll be computing forever to find an exact.
What happens if you have two regions that would lead up to W?
Pardon me?
If you have two different regions that are very far off.
Oh, yeah. Then unfortunately,
You have a
the
big
ball
ball.
will be big. So that's a good question. Can you have two, but
Yeah.
notice, if we have this inverse map which has smoothness, we can't have that happening, can we? Because whoops, right? Well, no, that depends on knowing that the states are well determined. Okay, but if the states are fairly well determined, and that's another theory, how you can recover the state from the data. And it turns out that you can recover the state well from the data through reduced models. I'll get to that in a minute. But generally speaking, we're gonna have a result that's positive in this direction. Okay, so let me give you the second way I can look at measuring performance, which would be more satisfactory to Bayesian guys. And this is what I would call a sketch algorithm. What I'd like to do is to determine a finite number of balls, very small balls, that cover completely all the parameters that can map into W. So if I could encode, if I could tell you, oh, the parameter is in one of these balls. And these balls have small radius, and there's only a finite number of them. That's a finer description. In the probabilistic world, you would say that the probability that it's not in these balls is zero. It has to be in these balls, so outerior probability, posterior probability is zero. And I know that it's in one of these balls. Then the question would be, well, have you done the best job? I mean, have you given me the smallest number of balls with that radius? And do you know that inside every one of those balls there is one of the parameters that give you the value W? If so, I think that's a pretty good description of what's going on, right? I would tell you the regions. And your question is, well, could you have a ball here and a ball way far apart? And my answer is that typically no. We'll get to results of that type in a minute. Okay, so that's the sketch. The sketch is to find a net, right? These points are a net, and they're a net in the sense that any parameter that gives you rise to W is close to one of these red points, right? And every red point has a parameter close to it that maps to W, et cetera, okay?
But in practice, will you get a clustering of the points that give you W like that? Does that happen?
No, no. Typically, all this is gonna be dependent on the regularity of A and all this, but typically, no. In fact, when we had that workshop, and Andrew Stewart and I were talking, they have what they call a small ball, what do they call it, vanishing ball? Their theorem would be analogous to your question in the stochastic setting. As you get more and more measurements, this is critical, by the way, Max, and that's, because if I give you 3 measurements, then of course you can't say anything about the parameter. But if I keep giving you more and more measurements, and they're good measurements, they're dense in some good way, then, yeah, you will squeeze down. Here we can prove that. In the Bayesian world, that seems to be a question to prove such a result. Yeah.
So, sorry, maybe this is coming up, but if you increase your measurements and you know what your approximation error to the true solution will be, say in the H1 norm, will your stability estimate immediately imply a convergence rate
Yeah.
for the radii?
Yeah,
Oh.
it's going to be on the next slide.
Sorry, yeah.
Yeah, but this is critical that the measurements are increasing, so you have increasing capacity to approximate the state. So there are 2 arms to this. You have, the measurement, okay, how well do they determine the state? And then now, given the state, we know in some sense we have uniqueness to go from the state to the parameters, so we're in good shape. So if the measurements, so if I think of here's the state, right? And here's my measurement, right? And it determines a very small portion of state. I can do well here, then I'll be in good shape back here because of the smoothness of my inverse map. So I'll be able to say there's a small region here and a small ball, right, in this case. In fact, I think the next slide discusses it. Yeah. So that's a strategy to solve the small ball problem, is to first use the data to find a guy in the state which doesn't necessarily satisfy the data, but all the U's that satisfy the data are close to that. So find a U hat, right? And it approximates all the UA that satisfy the data. And it does it well. And this will be possible with the better and better tolerance if I increase the number of measurements. And the measurements are well spread out. I don't want to get into that. There's a certain angle, and this angle. I don't want to get into that, what it means to have good measurements. That's another talk. But in any case, this is the strategy, okay? Use the measurements, find some U hat here in state that represents all the guys UA that satisfy the measurements, and then from U hat, use your inverse result to come back here. Because now you have, I put myself in a setting where the inverse map has some smoothness, so I know that I can't have 2 guys differing much mapping into something close here. So I can go from here back to here. And if you do that, you get what you wanted, a concrete estimate here. So this would be a ball in parameter space. I would have an a priori measurement on the size of that ball and know that anything that satisfied the data would be in this ball. And the size of that ball is going to be determined by this Lipschitz constant for the inverse map, 1, naturally has to appear. And secondly, how well did I resolve the state? R hat is how well did I resolve the state from the measurement. Okay? So this is good theory because it's an a priori performance. You know somehow you can achieve this performance, and now the question is, can you do it numerically? And why this isn't a numerical algorithm. It tells you how, it doesn't tell you how you're going to do all these arms, but it tells you what you should be able to achieve. And you asked a question earlier, is this the best you can? No, I don't know that. That's too tough of a question for me. Okay. Okay, so this problem, of taking measurements and going to the state and finding the states that can give rise to the measurements is a well-studied problem called data assimilation. And there are two main, there are certain least squares algorithms, first announced by these people and then studied by these people, where we give the quantitative performance of this. And they tell you how well you can do this problem. So I just want you to accept that there is a theory that says you can do this problem. We can tell you exactly how well you can do it. There's no wiggle room. It's very precise. It depends on two things: how well you can represent the solution manifold by a linear space. We usually represent the solution manifold by a linear space is through constructing a reduced basis through either a greedy algorithm or polynomial expansion. But the second ingredient is some measure of the quality of the measurements. There's a certain angle condition that appears. It tells you whether your measurements were well suited for this problem, because you could have a lot of measurements, as I said, they could be lousy measurements, not help you in this problem. So, but I don't want to get into the bloody details of that, so let's move on. Okay, so what am I interested in, and I'm coming closer to finishing. Apologize. So, the algorithms, here I want to tell you now about numerical algorithms for doing the small ball problem, but also for doing the sketch problem. Okay? I want to describe numerical algorithms for this purpose. And the numerical algorithms typically take the following view. They take parameter domain and they discretize parameter domain fine enough. Okay, this is going to be a problem because parameter domain is huge, overwhelm your computation. But the idea is that you discretize parameter domain, and for these discrete values you compute UA, and you compute your measurements, PWUA, and see whether you're close to W or equal W. And then of course you then, typically one looks only for one A, that's the small ball problem. And if you look for one A, as soon as you find a guy that is close to W within your computational tolerance, you stop. Okay, but this is numerically intensive, to search over parameter domain. Okay? And I want to describe to you better strategies than to do this. But one ingredient you're going to need if you take this approach is you need to have a fast way of evaluating whether PWA is close to W. So you need to measure this error. And the fortunate thing here is that this can be done very fast and very well. If you have two ingredients, you need a reduced model for the solution manifold, so you need a reduced basis, some linear space slicing through here that's close to the manifold. We know how to do that. We know greedy algorithm, so we can do that. The second thing is you have to solve that if you use adjoint equations, and these ideas go back to, I think, Ronacher, is that, would you use too when you, but anyway,
Yes.
yeah, if you use these adjoint equations, the nice thing is that you actually double the efficiency of the algorithm. So that if the solution reduced basis actually approximates a manifold with accuracy epsilon, then if you use these adjoint equations and to build a surrogate for E, something to compute E of A or an estimate E of A, you can double the accuracy to epsilon squared. And so you can have a very fast, efficient way of evaluating the error. So that's not the problem. The problem isn't the time that it's gonna take you, given an A, to evaluate the error. The problem is that you got too many A's. You're overwhelmed with the number of parameters that you're gonna have to set in. Okay. So our strategy here, both for the small ball and for the sketch problem, will be to test parameter domains to see for which PW of UA is close to W, but I'm gonna do this in what I call, what do we call this, divide and conquer or destroy, search and destroy algorithms. What we're going to do, and it's best to just describe it pictorially. So this is a discretization of parameter domain, right? And I'm now at the stage where I want to check which of these parameters give rise to a state whose measurements are close to my W. I can use that surrogate for E to do this in a rather fast way, but there are a lot of parameters, and I start with some coarse realization. I do this, and then I see, well, I have to go to a finer and finer realization to get my computational accuracy.
Well, may I interrupt you just?
Yeah,
To get
yeah,
an idea. So the value E is,
At the end, you maybe you didn't know, but you have to pay £1 for every question. And I don't know if that's gonna affect you. He's already £10 in. And he, yeah, well, I don't know how rich he is.
Or maybe you.
You're rich.
Or maybe you should pay £1 for every question.
I should pay.
For every question which you didn't answer.
I'm the boss, you're not. Okay, what's your question?
So this E is theoretically 0, right? Your E are,
For some A's, yeah.
no, what do you mean for some A? Yeah, I mean, there is an A such that it is 0.
Oh, yeah,
All right.
yeah. So, who's
No,
on first? Yeah.
except for the case that there is an interesting case where the data is not necessarily a solution of the.
Oh, yeah, it could be
differential
noisy
equation.
data, yeah.
And so you wanna do the best you can.
Yeah.
Yeah,
Yeah.
well, I'm talking about. All right.
Okay, so now, so this is my course resolution. Now, I compute E of A for every one of these A's, and I'll find that within the tolerance that I'm looking for, these red points are the only points where the error is less than the given tolerance eta. So I mark these points, okay? This is the search part. Now, what's nice is from this inverse theory, I actually know two things. From the forward and the inverse map, I know from the forward map that the value at these points nearby are close to the red values. They potentially still could be, well, they're not, they themselves are not, but territory near them could still potentially give a parameter which satisfies the condition that you get data W. The other thing I know is that if I'm far away from this, it can't be, right? If the error is big, let's say I'm at this point and the error, the current error is like eta, and this is like 5 eta or something, then I know that this point cannot be, and any territory near this point cannot give me a parameter that's close to the W I'm seeking. So what you do is you can put a lasso around these red dots and get regions, and you know now as you go further into search, the only place that there can be a parameter that satisfies your data, or is close to your data, is in the red region. All the other stuff has been thrown out. Can't possibly work because of the inverse. Because of the inverse theorem. If you see, if you get a reading here, let's say that your current tolerance is 1/2, okay? So all the red points gave you error E at most 1/2. Now, if you're out here, if the error is like 4, this cannot be, not only is that point not one of the points I can give you, anything nearby. Why anything nearby? Because of the stability of the inverse map. The inverse, right? Inverse is 4. Anyway, the stability of all this tells you that you can eliminate all these other territory outside. So that's what the search and destroy algorithms do. Now,
Sorry, how do you do this in infinitely many dimensions though?
Oh,
I can visualize
so-
this in a.
yeah, so you always truncate,
Right.
you always truncate dimensions, so typically you have like the affine case, where you have A bar plus some Yj psi j. And then you know that you can pick a capital D such that the
Okay, so you do truncate at some point.
back end of this series is so small that it doesn't affect the accuracy in the forward map within your computational tolerance, and then the same thing will be true for the inverse. So you always truncate at some D. And then you in fact quantize. In the search over parameter domain, you do not treat every variable the same. You do finer discretization in the first variable because it corresponds to a big psi. In the second variable, you do less fine, third variable, less fine, etc. So when you reach the dth variable, you have a very coarse realization parameter. Yeah.
Would it make sense to make Monte Carlo sampling over the parameter space?
Last slide, I'm gonna say something. Okay.
Let's say just
But back to the previous slide, now you're gonna refine in those red regions?
Yeah. The next step will say, okay, I haven't reached the accuracy I wanted. I mean, you start at a coarse accuracy. I have to refine. So I refine, but now I only have to refine the red region. I don't have to refine everything. And that's the saving. Okay.
Sorry. How do you do the clustering identification? How do you know that there are 3 clusters, and how do you create a ball around?
I take all the red points, and then I put a ball about every red point. So I originally had these points.
So if they're neighbors.
So, yeah, well, I put a ball about it, see, what I can do from the analytic theory that I gave, I can prove that if you put a ball about here, once you're outside that ball, and still nearby, you can't, if you're not close to one of those balls, so for every red point, put a ball. If you're not in any of those balls, then you can't have a parameter that satisfies your data, because if you're not in any of those balls, you're at a black point, and the black point, the error is big enough at the black point, 5 times the error you wanted, the smallest error, and so you can't have a parameter near a black point that satisfies
Should
your
it
data.
not be the other way around, you put the balls?
At every red point, I
The
put a
black
ball.
point, the black point, yeah.
Well, you can use it
I mean,
to throw away
Yeah,
territory.
but
Okay,
then,
we can go further on this if you want,
If you have some black balls in the
Yeah,
red region.
you have black inside the reds.
You have some black balls in the
There's-
red region.
the red region is not just red points. There's black points in this red region. Maybe you can't see that.
No, I know there are, but
There's
the
black
black point
points
can't
there.
possibly be.
And these black points are there because this is an ambiguity.
Yeah, but
Right, there's a
black points-
transition. Here, the black point, the value at this black point of E is so big, and E changes in a smooth way. You can't have E big and then immediately small because of this stability.
I understand that, but the black points should be all rejected, right? The balls should not
No.
near the black point,
No.
but should include it.
Yeah, the black point itself is rejected.
Yeah.
However, territory near the black point can't be rejected. So, I mean, what do you want me to do? Put a little ball around the black points or not? Okay.
So you have some additional parameters saying that there are candidates that currently are not chosen. That
Yeah, exactly. This is the way it proceeds, that, okay, we know that all the red guys are important. They're definitely in the ball game. We know certain black guys are not, can't be, they're far enough away, that the value of E at those points is thrown away. And there's an ambiguity region where we're not sure. And so we inflate around the red points, get this red region, and
So
that's,
there's another
reason as to
tolerance,
why.
there's another tolerance involved here to decide which black points to keep.
yeah.
For example, in the lower.
Yeah, which
lower
I haven't,
left, in the small region there, you kept one black point, but not the diagonal one.
listen, hey, Max, this is a little computation.
No, but I mean, that's
Cartoon
possible,
drawing.
but that's
I
possible,
gave it to graduate students to draw this. you
but that's
know?
possible, no, but that's still possible.
Yeah,
Because one black point is big.
yeah,
Right, so just one more question. So this is like your initial iteration, and you're gonna identify these 3 red regions and go
Yeah.
from there. So are you assuming that the way you've drawn the black points here is it's sort of, I guess to use statistical terms, space filling? So if my initial set of points that I searched over to identify those red regions had some gaps in it, I might have missed out a red point, which,
oh, I don't allow you to miss a red point. I stay on the safe side, it's like, you know, when you're
so
doing
you've
these,
gotta use a really,
I don't allow false negative, false positive, one of those things, right? I always require that if you threw away something, you're sure. There's not a parameter in there that could have been doing the job. All my ambiguities in the red region, it may be that I have these points, but they really couldn't. They couldn't. Did that answer?
So you're not allowed tiny red regions that fall between your grid. The grid's always fine enough that you can guarantee there are no red regions that you've missed.
If I don't have it marked as red, then there are none. Yeah.
Okay, so that means the grid has
Yeah,
to be
yeah,
fine enough to
yeah.
catch.
But then you will refine even more in the next step, right?
Yeah, and when I refine it, the next step, what will happen is I'll throw away some of these. Some of this I'll now be able to say, oh, wow, this was actually so far off being the true value W, I can throw it away.
But if the initial grid is so coarse that you miss the red point, then you're done, because you ignore the fact that.
No, there are always gonna be, red points, because,
No, I'm saying, if your initial grid is coarse, you may miss a region where if the grid was
that's a
fine, it
good
could be a
point,
red
yeah,
point.
so that's a good point, yeah.
Yeah.
You have to start out with a first grid, and that would require you to utilize this a priori analysis of, you know, what these constants are.
That was my question, so either you're throwing away
You're
black.
taking credit for his question?
I asked the question first.
1 pound,
No, but
it's a pound.
No, but you only understood what I
Either you're
said.
throwing away
You only understood
balls
what I
around the black points, or you somehow drawing the balls around the red points.
Oh, it's really throwing away balls around the black point,
Yeah, that's.
leaving you with the red territory.
Yeah, right,
Yeah.
so there could be, there could be a possibility that you have a region which doesn't contain any red points at all, right?
Yeah.
No, but it's not reflected on your picture.
What?
All the white regions.
There could be a region with no red points inside,
Well, these are regions with no red points.
No, but I mean, there
could be a red region with.
could be a
points.
red regions without red points inside,
Okay, maybe, yeah.
If the course is.
Depends how
Is
it
agreed.
depends how you do this lasso. But I say, what I do, yeah, you're right. I mean, you're saying the way to picture the algorithm is about every black point, you have a ball.
Yeah.
And you throw away
This
that
ball
ball,
and then-
and what's left is the red region. That is correct.
Yeah.
Now, some black points, the ball will be empty. I mean, there's nothing around it, right? Or some black points can have
No.
well, it'll always have 1 point in it, okay? But anyway, yeah, that's correct. So in reality, whoops, I'm throwing away territory, right? Search and destroy. Destroy is to throw away the territory.
So you can start with the grid where all the points are black initially, yeah.
Yeah.
And still you throw
Right.
something and then
Yeah.
you're left.
Okay, is that all sort of clear?
I think that there will always be, because of the assumption of these balls, that you will miss out on some small region that could have been possible. That you could have had a admissible solution. Because you're assuming that you have the ball, but they could have been slightly outside of this ball, that you still could have had solutions.
Well, let's say, you see, I don't know if we're on the same page, but you have your W, right?
Yeah.
And you've done a resolution that you know that at every black point, you have computed the up to accuracy at 1/2. The true value of the W at the black point.
Yeah.
Okay? And you know now that at the black point, the value you get for the error is 5. Well, you know this can't be the point you're taking. And then you also know that near that black point, you haven't changed much. Because you have all these analytical results. So the value is 5, and then maybe it dropped to 4 and then 3, but you're still safe, you know that those aren't. And that's the territory you throw away.
Yeah.
So you make this quantitative and you throw it away.
So let's say that the bottom right cluster, okay? So let's say that you have 2 blacks that could have been possible in the left corner, right? And then the...
Here?
No, down those 2 are possible, right? The 2 blacks, let's say.
Yeah.
But then you have 1 black that was not accepted that is just below it. So,
Yeah.
but you're creating a trust region that are some kind of sphere.
Yeah.
So it could have been some point exactly above that.
So let's say this value
No, the
was,
one on top.
this value was,
The one
the
above.
error is 2,
That one.
here the error is 1, and then I want to, you know, I can allow error 1/2 and say I don't know if the error is 1/2 with this discretization, whether it's in or out.
Yeah.
And then so like a level set, right?
Yeah.
But, you know, don't take this real seriously because, you know, that's for the programmer to, you know.
Okay, so
And
that
then,
is the, okay.
You know, the student comes back to you and says, you know, this didn't work. Well, I did it, I programmed it, doesn't work. And then you find little things.
But yeah, the concept makes sense. Then it's the algorithm.
Yeah, okay, so, here's the last thing. So if you're looking for a numerical display of this, you're not gonna see it because it's being programmed. And it's not ready for consumption. But what, I wanna point out one thing. You see, remember I started, this is the end, right? This is the last one, sorry, it took forever. But, you know, I started out saying I want algorithms that are optimal or near optimal or what I can do. Here, there is a certain optimality you can prove in these algorithms. That is, if in the sketch algorithm, remember I wanted to put balls about all possible points that could give you the value W or close to the value W that you wanted. This is to take this set, S eta, W, which is some set, and to find a covering of this set by balls of some radius, delta. This is a well-known concept called the Kolmogorov entropy of a set. And the number of balls you need is the covering number. And so if you say you want to have an algorithm produce these balls, you're going to have to need at least the covering number of the set number of balls. And we can prove that we're close to this number. So I can't say that I have the covering number S eta, but I can say S a constant times eta. I have something bounded by the covering number of this. So in some sense, at least I have a theoretical result that tells me my algorithm is not too bad. I mean, you can argue, you know, the numerics. There are other possibilities that you could have proceeded numerically, for example, with descent algorithms. Or some other procedure rather than search and destroy. The problem I have with descent algorithms is that This is although it's a convex minimization, it doesn't have very good convexity. It could be very slow. I don't see any good estimate for the computational performance. Now this, and I will answer your Monte Carlo a little bit. Well here, we actually made some advances on this work, and I want to mention it because I think that's some of your advertisement, right? When you're done, you want to say, hey, look, the program produced A, B, C. So I can provide a little bit there. One is, remember that we said a key to this is to find an approximation to this manifold, right, that's accurate. You actually want two things. You want this approximation to be accurate, but you also want it to match the data functionals in the sense that I told you there's a certain angle condition that if you take these data functionals, one approximation to the manifold may look good in its sense of accuracy, but be bad in terms of this angle, without getting too precise about it. And bothered us for a long time that if we know the data functionals, can we say what's the best reduced basis? Given that the data functionals are in your hand, you have a solution manifold, there are things called greedy algorithms, and the greedy algorithms are known to be, quote, optimal if you didn't have this data functionals floating around. And now what we were able to do is actually to give algorithms that are optimal even in the context when I have these data functionals W floating around. So that was one. Now on your point, random sampling. So this was another point. So one big problem in reduced bases is as you want to increase the accuracy of the linear space that you're generating, reduced bases are constructed offline. And you have a certain offline cost. They discretize the parameter space and do some computation, as do my search and destroy algorithms. And so you have this is a big problem, the offline cost. If you look at the usual way of doing the greedy algorithms, the offline cost grows exponentially with the accuracy you want. So if you want accuracy epsilon, the offline cost is going to go 2 to the 1 over epsilon to some power. It's going to grow exponentially. This is a big problem. What we were able to do here is to show that if instead of looking at parameter space and taking a discretization of parameter space to the accuracy you want, which grows exponentially, you instead do random sampling of parameter space. This makes sense, right? Take parameter space and to generate my reduced basis, rather than search all the parameters in a discrete, very fine discrete net, I'll just take a certain number of random guys and find the new snapshot that I'm going to add based on which of these has the biggest error. Then it turns out you can prove a theorem that this actually works. Now, it works in a sense of high probability rather than certainty. So that's, will you accept high probability? I would. If the probability is 10 to the minus 10, why not? So that is there. This same idea could be used in conjunction with this other algorithm. So in answer to your question, I wouldn't use this is Monte Carlo like, right? Random. But you also have the additional information that territory has been removed, so you really don't have to do random sampling in the territory that's removed. You only do it in the territory that remains. Okay? So, all right, I think that answers. And nonlinear reduced models. Well, in reduced models, you have this solution manifold, and this is your solution manifold, right? And a reduced model is, the typical ones are linear spaces, so you're taking the linear space here, trying to approximate manifold by the linear space. You can obviously do better if you take piecewise linear spaces, right? Which corresponds to certain parts of the parameter domain. You split the parameter domain into subdomains and use a linear space on each subdomain. You'll do better. And we can prove theorems and give algorithms for doing that. Okay. Terrible how much time I use. So, thank you.